Hello everyone. In this video we are going to discuss about an example of RSA algorithm. So here we will just take an example of RSA and we are going to solve it with the help of RSA algorithm. So RSA algorithm says first we need to choose two prime numbers. Choose two prime numbers. So let's suppose we select two prime numbers. So first one is P, which is equal to 7, and let's say Q is equal to 17. So because this is an example and we want to show this example, we took prime value as 7 and 17, but theoretically the RSA prime number should be very large. Now we need to calculate n, which is equal to P into Q, and which is going to be 7 into 17 is equal to 119. Now we are going to calculate Euler phi function phi n for this n. So this n is the multiplication of P and Q. Both P and Q are prime, so this phi n is going to be P minus 1 and Q minus 1. So it is going to be 6 into 16, which comes out to be 96. Now we need to select an E such that this GCD of E and phi n should be 1. GCD of E comma phi n should be 1, or in another words you can say that E and phi n should be co-prime to each other. So let's select this E and let's say the E is 5. So this also guarantee that E has an inverse modulo 96. E has an inverse modulo 96. Now let's say we calculate D. According to RSA, we calculate D and such that E into D is congruent to 1 mod phi n, which is 1 mod 96. And how we are going to calculate this D? This D we can calculate using extended Euclidean algorithm, EEA, which we have discussed in previous videos. So you can easily calculate this D using extended Euclidean algorithm, and this D comes out to be 77. So let's check that this D has an inverse modulo 96 or not. So E and D, so 77 into 5 comes out to be 385, which is 4 into 96 plus 1. So we can say that D and E are inverse of each other. Now we are going to calculate the public key of Bob, which is EB and which is n comma E, and the value of n is 119 and the value of E is 5. So this is public key of Bob and this is known to everyone. Now now we come to the private key DB, which is P, Q and D. So P is 7, Q is 17 and D comes out to be 77. So this is secret key or private key. This is only known to Bob. Okay, now encryption of RSA says how we do encryption. Encryption says we need to select a message M which belongs to Z of N, and it means Z of 119. So let's say M is equal to 19 such that the GCD of this M comma N should be equal to 1, or you can say that M and N should be co-prime to each other. So 19 is co-prime to 119. Now we will calculate. Now we are going to encrypt the message using EB, using this EB. This is, you can say this is small EB and this is DB. So we are going to calculate using this EBM, and it is going to be M to the power E mod phi n. So it comes out to be 19 to the power 5 mod 119. 19 to the power 5 mod 119. So this you can calculate using modular arithmetic properties. We have already done this. This can be calculated using modular arithmetic properties. So it comes out to be C is equal to, this is ciphertext, it comes out to be 66. So now our ciphertext comes out to be 66. Now similarly the decryption says d of db c is equal to c to the power db mod n, or c to the power d mod n. C is 66, d is 77, 62, 6 to the power 77 mod, so it is mod n. See, in the it is mod n, so it comes out to be 119. Let me check one thing. It's not phi n, it is mod n, so it comes out to be 119. So now when we solve it using modular arithmetic properties, it comes out to be 19. So now the ciphertext is plain text M is 19 and ciphertext is 66. So this verify. When we take plain text 19, we calculate ciphertext 66, and using decryption and taking the ciphertext 66, we calculate the plain text is 19. So this is how we can solve how the RSA algorithm is performed. So first we need to select two large prime numbers. So in this case, because we are doing everything manually, so I select two easy numbers so that the calculation is going to be easy. 7 and q, both are prime. Now we are going, in the next step we are going to calculate n, which is p into q, and in this example it comes out to be 119. Then we calculate phi n, p minus 1, q minus 1. Then we select an E such that E should be co-prime to phi n. E is 5 here. Then we calculate D. Then we calculate this D such that this E and D are inverses of each other and under modulus phi n. So this D comes out to be 77. Now this EB is the private key and EB is the public key and DB is the private key. Then we do encryption, and just to check or verify the encryption, we do the decryption like this. So this was an example of RSA algorithm, and this is how the RSA algorithm is performed. Now there are two main issues with RSA algorithm. First one is how to calculate large prime. I mean, how you can find a large number and you can verify that that number is a prime number. Because in case of like if we are talking about a number between 1 to 100 or even in fact 1 to 500, it is very easy to identify that that number is a prime number or not. But if we are talking about a 512 bit number, or even if we are talking about 1024 bits number, how we are going to check that that is a prime number, and how to get those prime? There is no specific algorithms for doing this. This is an issue because we need to calculate n. Why we need large prime? Because we need to calculate n is equal to p into q, and when we need to calculate this n is equal to p into q, so this should be the hard problem from n to find, because n is public and p and q are private. So this should be hard to find value of p and q with the help of n. That's why we need to choose the large primes. Okay. For example, if we take this p is equal to 3 and q is equal to 7, both are prime, and then n will be 21. So anyone can easily check the value of p and q by looking on the value of n. Because algorithm is public, everyone knows that in RSA n is the multiplication of two prime numbers. So that's why we need large prime to make this problem a hard problem, to calculate p and q with the help of n, because n is public and we want to make p and q as secret or private. But how to calculate these large prime? Because we are talking about the very large number like 512 bit prime, 1024 bits prime. So if we say that there is no defined algorithm, to calculate to find out that a number is prime. So what we do, we keep on doing the primality testing. So how to do this primality testing? So we do it with the help of primality testing, Miller-Rabin primality testing. So in the next video we are going to check about these primality testing. Thank you.